Hello. This is the start of Unit 4, and we will start with a term that is called a subring. In Unit 3, we have done about groups, and we have also started about rings, whereas in Unit 4, we will start with the definition of a subring. Uh, just like we have with groups, we have groups, and then we have a subgroup, and then we have a normal subgroup. Similarly, in rings, we will have a ring, a subring, and then something that is similar to a normal subgroup, but we will call it with another name, okay, as you will see later on. Okay, so let us see what is a subring. A non-empty set S is a subring of a ring if S is non-empty and it is a subset. And moreover, S should be a ring under the same operations of R. So let us see. So what do we have to do if we have to show that a non-empty subset is a subring? We have to show both conditions 1 and 2. But if you see condition 2, this condition 2, because it has to be a ring. And if you remember a ring, it already contains 10 conditions. Okay, just to remind you what are the 10 conditions. These are the 10 conditions of a ring. Remember, when we were dealing with rings, this one belongs to R, but because we need to prove the conditions of a ring for the subset, so that's why everything belongs to S. Okay, so these are the 10 conditions that are contained in condition 2. And this 10 condition, okay, for now you can forget it, okay, but in the modern definition it is there, okay, but for this course it is best if you prove on it only up to number 9. Okay, you will see why. Okay, so what is an example of a subring? For any ring R, you take only the 0 element. Remember that a group, it has an identity element E. So a group always has an identity element E. A ring will always have uh, a ring will always have the 0 element, which we will denote it by 0. It is the additive identity, if you remember. So you remember, if you take only E, it will be a subgroup of G, right? So similarly over here, what we are saying that if we take only 0, it will be a subring of R. Okay, so let's see. For any ring R, show that S equal to 0 is a subring of R. So clearly it is non-empty. It is non-empty because S is equal to 0, right? It has the element 0, so that is why it is non-empty. And also it is a subset of R. That is clear. Okay, so now we need to show the 10 conditions that are contained in condition 2. So what do we have to start? Okay, again, let us see what do we have to do. You see this? A, B, and C belongs to S, right? So that is how we will start. That A, B, and C belongs to S. But S over here, it contains only the element 0. So it has no choice. A and B and C, they all have to be equal to 0. So A is equal to 0, B equal to 0, and C equal to 0 when A, B, and C belongs to S. I hope that is clear. Condition 1, A plus B, both of them are 0, so it will belong to S. And we also have A plus B plus C. It will be equal to A plus B plus C, because both of them, they are equal to 0. 0 is already there, so the additive identity, of course, it belongs to the subring. If A belongs to S minus A belongs to S, if A belongs to S, because A equal to 0, so if A belongs to S, so A equal to 0, hence minus A will be equal to 0, also belongs to S. A plus B will also be equal to B plus A, because A and B are 0, so both of them will be equal to 0. Similarly, condition 6, 7, 8, and 9, they hold. Okay, just see 6. A dot B. How much is A dot B when A and B are 0? It will be 0, right? So it belongs to S. S is 0. Keep that in mind. In our case, okay, for that example. Similarly, A dot B dot C will be 0. this right hand side will be 0. So condition 7 also holds. Similarly, condition 8, both of them will be equal to 0, right? Similarly, condition 9 will also hold. So that is why it will be a subring. A condition 10, it's not required, but anyway, over here, okay, do not write it down. Okay, for in this semester, it's not required. Okay. Okay, so if you see that if you have to prove that something is a subring, you need to prove so many conditions, right? 10 conditions in condition 2 only. So that is why we have this theorem that will help simplify things. Let's see. This is the theorem. S is a subring of R if and only if instead of 10 conditions, we only have the 3 conditions. Okay, the proof of this theorem, do not worry, okay, I will send the notes. It's not so much required, okay, but have a look at it. It's similar to the things when we were doing in groups. The only difference is that here we are dealing with 2 operations. Again, go through the proof. I will send it in the notes. Okay, but the 3 conditions, you have to remember them, okay, as you will see. Okay, let us just see what the 3 conditions say. It will be a subring if it is not empty. It will be a subset. A minus b belongs to S, and a dot b belongs to S for all a and b belongs to S. So if you have to prove something is a subring, you need to prove condition 1. For condition 2 and 3, you will start with let A and let B belongs to S. I hope that is clear. Again, the proof, I will send it in the notes. So let's see. Let us try to use that theorem to prove this example. Show that S is a subring of Z. Okay, clearly it is not empty because it has some elements, and moreover it will be a subset of Z. Z is a set of integers, so it will be a subset of Z. That is clear. So for condition 2, just like I say, we need that A and B belongs to S. After a few lines, we need to have A minus B belongs to S. So these are the few lines that we have that are there. Okay, so A and B belongs to S. If you see the set S, it contains only even integers. So A and B are even integers. Again, this second line, it will depend on the set S. Sometimes it will contain of multiples of 3, sometimes multiples of 4, and sometimes if it is not Z, maybe over here it is the set of matrices, then over here also will be a set of matrices. Okay, so you have to be very careful with this second line. Okay, you have to see what the set S is. Do not worry, I will give you some exercises. You can try them on your own. Oh, okay, so this one, if A is an even integer, so it will be divisible by 2, that is A. It is a multiple of 2, and B is a multiple of 2. A minus B, it will be equal to 2x1 minus x2. So it will be a multiple of 2, that is why it is even, it will belong to S. Similarly over here, A dot B, 2x1, 2x2, you will have this, it will be even, it will belong to S. Hence, it will be a subring. So instead of proving the 10 conditions, now we only need 3 conditions to show that S is a subring. You can try this exercise on your own. It is not so much difficult. So what I want to say over here is this. Okay, so S, if you remember, S equal to 0 and S equal to R, they are subrings of any ring R. And these are called the trivial subrings of R. So a ring, it always has 2 subrings, at least 2. These are the 2 subrings that it will always have. In addition, it may have some more, but at least you are guaranteed that it will have 2 subrings, which are called the trivial subrings. Okay, so now that we have learned, okay, again let me remind you, we have group, and then we have a subgroup, and then we have a normal subgroup, right? In rings, what do we have? We have a ring, and then we have a subring. In place of a normal subgroup, what we will do, we will be having cosets. I made mistake. we will be having ideals. In place of normal subgroups, we will have something that is called an ideal. It behaves similarly to a normal subgroup, but it's just that in the case of rings, we will be calling it ideals. Okay, so let's see the definition. And you must remember that in a ring, it may not be commutative. That is, a dot b, it may not be equal to b dot a always. Sometimes it may be equal, sometimes it may not be. So that is why we have something that is called a left ideal, right ideal, and something that is called an ideal. So let's see the definition. I is a left ideal of a ring R if it is non-empty, it is a subset. A minus B belongs to I for all AB belongs to I, and RA belongs to I for all A belongs to I and R belongs to R. Okay, do not worry, when we are doing examples, you all will understand better. Similarly, a right ideal, it will be similarly. You see the condition 1, condition 2, they are the same. So the only difference between a left and a right is that this R, when it is left, R is from the left. R belongs to R. Remember, A and B belongs to I. Always remember that. A and B belongs to I. R belongs to R. Again, let me remind you, over here we are just using notations. So instead of A and B, you may as well use X and Y. It doesn't really matter, X1 or Y1. So if you have to use this one instead of X and Y, you will say X minus 1, Y belongs to I for all X, Y belongs to I. It doesn't really matter because we don't know what the elements of R looks like. So that is why A and B, they are just notations, okay, for the elements. You may as well write it with a capital letter or with X1, X2. It doesn't really matter. Similarly for R, okay, you can even do it with S, you can do it with X. It doesn't really matter, but the condition that R belongs to R, it's important. So we have seen what is a left ideal, what is a right ideal, what will be an ideal if it is left as well as right. So the first and second conditions, they are there. The third condition from the left ideal, it's here. The third condition from the right ideal, it's here. So it will be both a left as well as a right ideal. That is why it will be called an ideal, or sometimes a two-sided ideal. Okay, maybe I'll just write here, two-sided. Okay, so let us see some examples. I equal to 0 is an ideal of any ring R. Okay, prove it. Okay, it is a subring. If you take only the 0 element, it will be a subring, but it will also turn out to be an ideal. Just like in the case of E, remember? E, it is a subgroup. It will also be a normal subgroup if you take only the element E. Similarly, if you take only the element 0, it will be a subring and also will be an ideal. Okay, so let's see. Clearly, it is unequal to, it is non-empty, and it is a subset of R. That is clear. So to prove the second condition for a left ideal, remember, for a left ideal, we start with let A and B belongs to I. So that is what we are doing here. Let A and B belongs to I. We need to show that A minus B belongs to I after a few lines, but I, it contains only the element 0, so that's why A equal to 0, and B is equal to 0. A minus B, it will be this much, it will be equal to 0, hence it belongs to I. Okay, for the third condition, A belongs to I. Oh, sorry, over here it should be R. Okay, R belongs to R. R belongs to R. Okay, so A belongs to I. It consists only of 0. How do I know that? Because it is given. R, okay, but you cannot put R to be equal to 0 because it belongs to R. Over here, you don't know what the ring R is. Okay, it may contain only 0 or it may contain some other things. So that's why you cannot write down R equal to 0. Okay, be careful. So A equal to 0. RA will be, R times 0 will be 0, it will be equal to 0, belongs to I. Similarly, AR will belong to I. hence it will be an ideal. You can try this one as an exercise. Similarly for this one, show that if it is a left ideal, then it is also a right ideal. The hint for this one is that AR will be equal to RA, right? AR it's equal to RA. That is the hint. Another exercise. Remember, any subgroup, it contains the element E. Any normal subgroup also contains the element E. Any ideal will always contain the element 0. Let's see. Prove that if I is an ideal of R, then 0 belongs to I. If I is an ideal, because it is an ideal, it has to be non-empty. That is condition 1 of an ideal. You will see. Just see the condition 1. See here, I is non-empty, right? Right there. So what do you mean when you say it is non-empty? When we say that it is non-empty, so that is why we'll have an element, has an element. It has an element, we will denote that element by A. Okay, you can even denote it by B, it doesn't really matter. Okay, so taking A equal A and B equal A. Okay, A equal A belongs to I. B is also equal to A, which belongs to I, because it has this element A. Okay, by condition 2, let us see condition 2. What does it say? Condition 2 says that if A belongs to I and B belongs to I, then A minus B belongs to I. So that is what we are doing here. Let's see. A belongs to I, B belongs to I, so A minus B belongs to I by condition 2 of an ideal. Hence, A minus A belongs to I because B equal to A. That is 0 belongs to I. That is clear. Okay, another exercise for an ideal. Prove that if I is an ideal and if A belongs to I, then minus A belongs to I. This is very simple. A belongs to I, then A minus B belongs to I. This is condition 2 of an ideal. Okay, but 0 belongs to I. How do I know that? Because I is an ideal, it will always contain 0 from the above exercise. And A belongs to I. When A belongs to I and B belongs to I, then A minus B belongs to I. Hence, minus A belongs to I. That is also clear. So, two very easy examples. Okay, now what we will do is we will do construction of left ideals and right ideals. This is very important. Okay, because sometimes in the proof of theorems, you need to construct ideals. Okay, how will we do it? One of the ways that we can construct ideal, okay, if you have any ideal, we can just say that I1 equal to 0 is an ideal, and similarly I1 equal R is an ideal, right? But if we need other ideals, how will we do it? Just like if we need normal subgroups, how will we construct? Over here, if we need ideals, how will we construct them? So this is the theorem, I should say. Okay, let's see. Let R be any ring with identity. Identity, it means it contains the element 1. I equal RA is a left ideal. I equal AR is a right ideal. Remember that an ideal is a set. An ideal is a set. So when you say I equal RA, it means that RA has to be a set. How do we define this RA? RA will be set of all element X, which can be expressed in this way. X equal RA, where R belongs to R. So multiply all multiply A by all the elements of R, include that in the set. Okay, it will be a left ideal if you multiply it from the left. And if you multiply A from the right by R, it will be a right ideal, this set. Okay, proof. I will be doing the proof of 1, the proof of 2 and 3. It will be your work. Okay, so let's see. Remember, we have to show that I equal, over here what I'm doing. Let me see. Okay, I am doing it for RA. Okay, it will be LF ideal. So let's see, clearly it is non-empty. How do I know that it is non-empty? Because this one 1 times A, 1 is from R, right? 1 is an element of R, A is over here, so A, it can be expressed as 1 times A, so it will belong to RA. So that's why I, which is equal to RA, it will be a left ideal. Okay, and will be a subset. It will be a subset because if you take any element of I, then you can express it as this from here. I is equal to RA in this case. Okay, for the first one, I will be equal to RA. So X will be equal to RA, so it belongs to R. R belongs to R. If you remember, from here R belongs to R, and also A belongs to R because it is given. Okay, so that concludes number 1. Condition 2, that xy belongs to I. After a few lines, we have to get x minus y belongs to I. I is equal to RA. Again, I repeat, over here in this example, I is equal to RA. X comma y belongs to RA, so x will be R1A and y will be equal to R2A. Some of you may be confused. You may write it as this, RA and y equal RA. Okay, this is wrong. Okay, why is it wrong? Because we don't know what this element that comes from R. Okay, we don't know what it is. That is why for some element x, you may have a different R, and for y, you may have a different R. Okay, similarly, x minus y will belong to RA. Because R1 minus R2, it belongs to R. Condition 3, it's again very simple. R belongs to R and x belongs to I. Because x belongs to I and I is equal to RA, so x will be equal to R1A. So Rx, okay, just follow the steps, you will get this. Okay, so this is how we can construct a left ideal. Similarly, condition 2 and 3, you can try it by yourself. That is the way that we will construct right ideals. Okay, let me just give you an example for this one. Okay, suppose you have the ring of integers z. Okay, R is equal to z. Okay, which is equal to minus 3, minus 2, minus 1, 0, 1, 2, and so on. Okay, so how will we construct a left ideal? We just take A. Take any element A. You can take A equal 1, A equal 2, equal 3, equal 4, equal 5. Okay, let us take A equal to 7. You can even take it with the negative or 0 or any number. So that is why we can construct so many left ideals or so many right ideals depending on our choice of A. So how will we construct a left ideal? It's this, RA. Multiply all these elements by 7 from the left. Okay, multiply all the elements of Z by 7 from the left. Sorry, from the right. Then it will be a left ideal because R, it is in the left, so that's why it will be a left ideal. So this set, okay, if you multiply, you will have minus 21, minus 14, minus 7, 0, 7, 14, okay, and so on. This one will be a left ideal. Similarly, you can construct a right ideal by just choosing the ring and by just choosing an element. Okay, and also now we will come to this important one, operations between two ideals. Remember, if you have two subgroups, you can intersect them, you can form the union. Okay, and we have the theorem that intersection of two subgroups, it is a subgroup. Intersection of two normal subgroups is again a normal subgroup. Similarly, over here, intersection of two ideals is an ideal. This one, I will leave it to you. Okay, you just need to prove the 3 conditions for I1 intersection I2. Similarly, this one, I1 plus I2, Because intersection, if it has to be an ideal, it has to be a set. Intersection of two sets, it is a set, so that is why the intersection poses no problem. But for number 2, we have introduced a new symbol, addition of two ideals. How will we define addition? Okay, it's by using this x, such that x is equal to a1 plus b1, where a1 belongs to I1 and b1 belongs to I2. That is how we will define addition of two ideals. Again, this one you can try it. Okay, if you cannot do it, then you can always ask for some help. This number 3 is what I will do. Okay, because it is a product of ideals. If you see the definition, it is not just, over here in addition it's just x equal a1 plus b1, but over here it's not a1 times b1. Okay, you have some other things as well. Okay, a1 b1 plus a2 b2 plus a and bn. Okay, I will do the proof for this number 3. Okay, so let's see. How will we define it? We define it this way. Over here, even though I'm writing it as a and bn, what we are doing here is that this sum, okay, it should end. It should be finite. It should end in a finite number of steps. Just like over here it ends in n steps. It may end in 3 steps also. Then x, it will be in I1, I2. If it ends in 2 steps also, it will be there. If it ends in 3 steps, 4 steps, 5 steps, or even 100 steps, as long as it ends finitely, then that element will be here. If it is, it can be expressed in this way, and if it ends finitely, okay, then that element will be here. You just have to be very careful over here. The first, you see over here you have n terms. You have n terms. You may have only 1 or 2 terms, it doesn't really matter, but each term comprises of 2 elements. You see, this term also comprises of 2 elements. The first element, it should come from I1, and the second element should come from I2. That is why all the A's, AI, A1, A2, A3, A4, AN, it should come from the first term, that it belongs to I1. The second term, the second element, it should come from I2. Okay, just see. Okay, so we need to show that I1, I2 is not empty, and all the 3 conditions for all the 4 conditions for an ideal are satisfied. So let's see the first one. 0, it can be written as 0 times 0, right? 0, is it an I1? Yes, it is in I1. This 0, the first element. Yes, it is in I1 because I1 is an ideal. This second 0, it is in I2 because it is an ideal. So 0, because it can be expressed in this way. Okay, so it can be expressed in this way, but it ends only in 1 step. That is why it belongs to I1, I2. So that's why it's not empty. And I1, I2, it is a subset of R. Okay, that is clear. Okay, number 2. Let x and y belongs to I1 and I2. So x, it can be expressed in this way. It ends in n steps. And y, okay, it can also be expressed in that way, and it ends in m steps. You have to be careful. The first element, it should be from I1. The second element, it should be from I2. Similarly, over here, the first element should be from I1. The second element should be from I2. So x minus y, this is in n steps, this one in m steps. So over here, total, it will be n plus m steps. N is a finite number. M, it is a finite number. N plus m will also be finite. That is why x minus y will belong to I1, I2. That is clear. So the third one, that x belongs to I1, I2, and R belongs to R. Okay, we are proving the conditions for an ideal. Okay, just see the conditions for an ideal if you don't remember. But this is the third condition. X belongs to the set that we want to prove that it is an ideal, and R should belong to R. If X belongs to I1 and I2, then it will have that form as in the. If you multiply it with R, you will have this. So if you see this one, now we are having 3 elements in each term, right? But if we have to show that it is in I1, I2, we need to group it into 2 elements. So that's why we are grouping it in this way. Why do we group it in this way? Because RAI, it will belong to I1, because I1 is an ideal. Okay, remember, if A belongs to an ideal I1, you multiply it by R, then it will also be in I1. Okay, because that is the condition for an ideal. A1, if you see over here, all the AI belongs to I1, right? So if you multiply by R, RA1, it will belong to I1. So that's why we have this. Similarly, RA2 belongs to I1. I hope that is clear. So Rx, it can be written in this way, and it ends after n steps, right? So that's why will belong to I1, I2. Similarly, this one, if you see, it will belong to I1, I2. Even if you multiply X from the right by R. Okay, so this is the last exercise for today. Show that if the multiplicative identity 1 belongs to I and I is an ideal, then I equal to R. This is very, very important, okay? In fact, I should mark this one with a star. Okay, it is very important because once you have 1 belongs to an ideal, then the next line you can immediately write I equal to R. So the proof, it's very simple. We have I, it is a subset of R. If we need to show that I equal to R because it is a subset, because they are sets, we have to show that one is a subset of the other and the other is a subset of the first one. Okay, so I is a subset of R. That is indeed true because I is an ideal. Now we just need to show that R subset of I, that R belongs to R. But A equal 1 belongs to I. How do I know this one? From this. If A belongs to I, then you multiply it from the left or from the right by R, then it will belong to I because I is an ideal. So R belongs to I, R belongs to I, hence R will be a subset. We have started with an element R belongs to R. We have shown that it belongs to I, hence R will be a subset of I, hence I equal to R. I think that is enough for today.